Now, we have seen how to work with fractional exponents, but sometimes when you simplify, you are left with a fractional exponent that you cannot reduce without having to approximate. Like you have something like the square root of 2. The square root of 2 is not a rational number. It's irrational. If you type it up in the calculator, you get some 1.41 something. And sometimes to represent the numbers, it helps to just leave it as it is and work with it. So square root of 2, if you leave it as square root of 2, we all know what it means. And so in this part of the course, we're going to learn how to work with these sorts of radicals. Now, we can call them radicals because they are missing something. Like if you square the square root of 2, you get 2. And so you get a whole number. So we're going to work on things of that sort. So a radical expression is an expression that has a root sign. Like this one, this is also a radical expression. And so we will discuss how to add, subtract, multiply, divide, and then rationalize radical expressions. So here, when you have a quotient and the radical occurs in the denominator, we will want to rationalize. And then sometimes we can solve equations that have radical expressions. So what rules can we use to simplify them? Let's start with some real numbers. So A and B are numbers, and M and N are natural numbers, and we don't want N to be 1 because we're taking the roots, the nth root. If you take a first root, you are not taking any roots. So we will deal with only the positive roots. So if N is even and we take the nth root, we return just the positive number. For instance, the square root of 4 is going to be 2. We'll throw away the negative 2. If it's odd, we don't have any problem. So those are things to keep in mind. Now, we can multiply. So you can have the nth root of A times the nth root of B gives me the nth root of AB. The nth root of A divided by the nth root of B is the nth root of A. The nth root of A over B is the nth root of A divided by the nth root of B, provided B is not 0. And the last part is the nth root of A to the M equals the nth root of A all raised to the power M. Now remember, we cannot add radical expressions. I know 2 plus 3 is 5. But the square root of 2 plus the square root of 3 does not equal the square root of 5 because the square root is not linear. It's not additive. So I have just said what I wrote down. You cannot add or subtract distinct radicals. If they are not the same, then you can't add them. So the square root, the root of A plus root of B does not equal root of A plus B, neither the difference. Like this one, the cube root of 2 is a certain number. It's not 1. It's not 2. The cube root of 1 is 1. But the cube root of 2 minus the cube root of 1 is less than 1. So it cannot be equal to 1. So what we do is we treat them like variables. And so we reduce the system and then we combine like terms. So we will see in this case, this is going to be the square root of 80. Well, square root of 80, we can't really do much with it until we get as many squares out of it. But the only square I can think of now, well, I can think of a few. I can think of 16 and 5. So I can think of 16 with 5. So that's square root of 16 times square root of 5. Square root of 16 is 4. So this becomes 4 times the root of 5. And we leave it this way. So we'll use that to reduce all of these. With these ones, we will multiply them out and simplify. So we'll get to that as well. So in the pretest, I put a problem there where we had to rationalize the denominator. And the point is to express a radical expression in a form where the radical does not appear in the denominator. So we call that rationalizing the denominator. Okay, so for instance, we can write 1 over root 2 as square root of 2 over 2. And you've seen this before. If you've seen cosine of pi over 4, in some books, it's written as 1 over root 2, but in other books, it's written as root 2 over 2. They are the same. And the way we obtain the second expression is, notice that I have a root 2 in the denominator. So I multiply by a fraction which is 1, but it's written as root 2 over root 2. And these give me 2, and I have root 2 over 2. Similarly, if I have 3 over root 12, and I simplify the root 12 and write it as 2 root 3, the radical is root 3. So I multiply by root 3 over root 3, and I end up getting root 3 over 2. And the key thing is that they represent the same number, the very same number. So if you have an expression like this, you can't multiply by root 3 over root 3. I mean, you can, but it will not help you rationalize it, because every time you multiply, you have a root 3. So what we do is that we multiply by its conjugate. So conjugate in this case, because this is the square root of 3 minus 1, its conjugate is the square root of 3 plus 1. And it's picked so that when you multiply, at the bottom, you have a difference of squares. If you have a difference of squares and the radical is a square root, this radical disappears because of the squares. So down here, we use the fact that a plus b times its conjugate a minus b is a squared minus b squared. So this will give me root of 3 squared, which is 3, minus 1 squared, which is 1. And then we simplify the top and we end up getting this. And you can plug this in your calculator and see that this expression is precisely this one. So in the examples, we will see how to rationalize the denominator. This isn't an interesting one because now it's not squares. It means that we may have to do multiple steps. But we will see how to work those out. And then we will see how to use these ideas to simplify other expressions. So we have quite a lot to discuss in the class. We'll see you soon.